Okay, guys. Okay, guys. I hope I am audible now. Can someone please confirm? Cool. So let's start with today's session. So today is a combined session where we'll be looking around the first three lectures of the ARAM lecture series, and we will be taking this in three short sessions of 50 minutes each. Yeah. So let's start the session. I am Master Siddesh Yadav. I'll just give a small introduction about myself because many of you might not know me very properly. So I was the project lead of Asia's largest student-built hybrid rocket engine in Team Abhyuday. That was rocket team of IIT Madras. I led that project for 2 years. I completed my internship at ISRO at Liquid Propulsion System Center, and yeah, is an upcoming research paper. Okay, I have done. I'm currently doing internship at the TU Munich in Germany. I am a young research fellow at IIT Madras. I'm a member of Rockets and Missiles Lab at IIT Madras. I have attended two conferences and publishing in the proceedings of both of them. That is UCAS in Europe, UCAS and IWCP. Both are propulsion conferences, combustion propulsion conferences in Europe. If you have not joined the WhatsApp group, so you can maybe scan the QR code, join our WhatsApp group. Next thing is starting with the small part about rockets. I have written this thing. I just want some volunteer maybe to read this for me. Anyone, please. Someone please read this for me?
Shall I read it?
Sure.
Rockets are among the greatest technological marvels ever created by humankind. From launching satellites that connect our villages to the world to exploring the moon and Mars, advancement in rocketry have helped India reach for the stars. Thanks to ISRO's pioneering work, from the PSLV launching over 300 foreign satellites to Chandrayaan and Mangalyaan, making every Indian proud. Our nation has shown what determined young minds can achieve. We believe India's next generation of rocket scientists, engineers, and innovators are already among us in colleges, schools, and workshops like this one. This workshop is specially designed for students and passionate engineering enthusiasts who wish to get a strong foundation in rocket motor design. We'll get to work hands on with real hardware, understanding how a rocket is built, and witness the thrill of launching a rocket with our own eyes. If you dream of working at ISRO, building rockets for India, or one day putting an Indian flag on Mars, this is the perfect place to begin your journey. Come, let's ignite minds and build India's rocket future together.
Very good. So the problem with us in our nation is that we lack a lot of skill set in the initial phases. That's why maybe people are unaware of a lot of terms. I mean, professionally, so I have seen a lot of people making solid motors, but doing it very unprofessionally, unsafe, and without proper calculations, and ending up making a rocket engine with an ISP of 87 seconds. So to avoid such things, this is the session to get you the skill sets. So questions that people generally ask me is, how do I get an internship at ISRO? How can I get first internship at rocket propulsion? That is most difficult thing. How to get competitive for jobs at Agnico, Skyroot, ISRO, RFA, DLR. These are German companies, but there are a lot of Indians over here. How to make a perfect resume to get job in rocket propulsion? How to get into European universities as a researcher? How to get job in Europe as a propulsion engineer? There are a lot of opportunities, lot of possibilities. Most uh, the thing is that we are mostly unaware of opportunities and stuffs going around the world. We might know what is going around in our state, district, maybe sometimes nation, but rarely, I mean, very less people around us in our student rocketry committee knows actually what's going on around the world in the domain of rocketry or amateur rocketry or professional rocketry stuff. Solution to all questions is this workshop. As I mentioned earlier, there will be weekly sessions at affordable cost. That is around 15 rupees to 50 rupees per session. Depends if we have some special sessions, we will be charging more. And If you have my session, then yeah, it will be 15 only per session. And this is a 100 lecture program where we'll be where I'll be personally teaching you all kind of rocket and some high speed air breathing devices, which you'll be seeing further in today's session. And there will be additional sessions like how to read research paper, how to write your own research paper, because I have written my own, so I can guide you on the same. And also about the publications, where to publish, where not to publish, the impact factor, etc. You will also learn to design your own rocket engine, either solid, liquid, hybrid, or high speed air breathing. We will be doing some simulations in the future. There can be university collaboration to start your own rocketry team, because I have led student rocketry team in almost everything, so I can actually guide you on how to start your own rocketry team, do integration in the domain of propulsion airframe, propulsion avionics, propulsion telemetry, etc. Let's leave the next point. Coming to the next point, yeah, there in later in the course you'll be learning coding to develop your own prediction tools for rocket engines. That's what I do as of now. I develop my prediction codes, and I do not actually test the engine and update the model. I just make prediction codes based on the previous testing and update the model, and it works very well. So there will be machine learning to make good prediction tools, and if someone wants a recommendation letter from me, I can give. Not an issue for me. I mean, some well-performing students, or maybe I can recommend you to some good places around the world. So, starting today's session, I will be talking about four different topics. First will be introduction to conventional rocket propulsion system. Second will be introduction to air breathing high speed propulsion devices, that is ramjets and scramjets. Third is a very complicated thing, very less people in the world actually works on it, and this is the domain in which I want to pursue my career, that is combined cycle engines, also called as RBCC, DRBCC, TBCC, TRRE, etc. These are basically rocket based combined cycle engines, dual rocket based combined cycle engines, turbojet based combined cycle engines. And then we will be talking a little bit about upon the opportunities available. Let's see, mostly we will skip this part, because I don't want to shift much apart from technical discussion. This slide has no use. Yes, starting with the classification of rocket propulsion system is divided in two parts. One is thermal, one is non-thermal. What is the difference? Thermal, the definition of thermal is related to heat. So thermal means you release heat energy. Basically, you burn something or you have some form of energy, you release it in the form of heat, and that heat is used to, I mean, that heat energy in the form of thermal energy is converted in the form of kinetic energy with the help of nozzle, and you get high thrust. That is thermal. Non-thermal is everything except the thermal energy, that is solar, cold gas thrusters, electrical beam thrusters, nuclear ion based, etc. So this is the basic difference between thermal and non-thermal. We will be looking in thermal propulsion system, specifically in chemical propulsion system in this course. As of now, later we can see other systems as well. So thermal also, there is chemical, there is non-chemical. These are the ways to produce the thermal energy. It's like chemical is like you use the chemical energy to make a reaction, convert it into thermal energy, basically exothermic reactions. And in chemical, you have monopropellant, bipropellant. Now I will give you a small example. You have a candle burning. Take an example of candle burning. You have a candle burning and you put a glass on it. So what happens basically is the candle stops burning. This is a very important example, because if you observe observe the experiment, what is happening here is you are stopping the oxygen flow by putting the glass on the candle, because when you put the glass there is no more oxygen coming to the candle and it stops burning. It means that to burn anything, okay, from now onwards I will use the word combustion instead of burning. It means to burn anything you need two substances. One which can burn on its, I mean, which can burn, that is called as fuel, and another which can support burning, that is oxidizer. So if I say fuel, then you take it as something which has the capability to burn, and if I say oxidizer, in simple words, you can say as something which can support burning. Without any of this you cannot have a combustion or you cannot have a burning. So it means that you need fuel and oxidizer. So for a combustion to happen, so if the fuel and oxidizer both are different chemical substances, for example KNO3 oxidizer sugar as fuel, then you call it bipropellant. Propellant is basically fuel and oxidizer together are called as propellant. So if I say propellant, then you should know that fuel and oxidizer together I am calling as propellant. Now, if both the fuel and oxidizer both are different chemical substances, then you call it a bipropellant because two there are two different chemical substances like KNO3 and sugar. But if the fuel and oxidizer both are a single chemical substance like the nitrous oxide, you can say, or ammonium perchlorate, what happens in a monopropellant is a single substance, it undergoes decomposition, and because of the decomposition the bond breaks and it releases energy. That energy release is basically used for combustion, so that is a monopropellant. It's a decomposition reaction. In bipropellant, two chemical substances reacts, form multiple products. The reaction is exothermic. And just a minute. Okay, I think almost everyone is in the lecture. Cool. So yeah, and then we call it a bipropellant. Coming on to the, and yeah, bipropellant you can classify, I mean, you can classify as solid, liquid, hybrid. Solid is basically both fuel and oxidizer in solid state or in the solid form at room temperature. Liquid means both the fuel and oxidizer are in liquid state at room temperature. Hybrid means one of the fuel or oxidizer is in solid state and another is in liquid or gaseous state. Then you call it a hybrid propellant. We will be looking at solid, liquid, hybrid, and two other stuffs in the upcoming slides. I will explain you the next two stuff, that is the pressure fed system and the pump fed system. So pressure fed system is basically you have a pressurized gas which is running your oxidizer. I mean, I'll simply tell you, in order to have a combustion in the combustion chamber, you should have oxidizer and fuel coming inside. So in order, and you know that gases or liquid they can move because of the pressure difference. So if your pressure difference is created with the help of high pressure gas, then it is called as a pressure fed system. If your pressure difference is created with the help of a pump, like we do in the rural villages where you have a pump which extracts the water, so that is called a pump fed system. Simple as that. Okay, just a minute. Cool. So this is about the pressure fed and pump fed systems. Coming on to the rocket theory, rocket operates based on the Newton's third law of motion. That is, one thing goes out, that is the hot gases, and it pushes the combustion chamber, which in return pushes the airframe or the body of the rocket, which moves the whole rocket. Chemical propulsion uses fuel and oxidizer to produce high-speed exhaust gases for thrust. As I explained you, solid propellants, yeah, and this is basically explaining the solid, liquid, and hybrid. That solids are a mixture of fuel and oxidizer, both in solid state, liquid in liquid, and hybrid one in hybrid one is in solid, another is in liquid. So this is the basic thrust equation which you can see on the screen. F equals to m dot v exit plus p a into p minus e p a. We will be learning about this in the future sessions. I mean, in this second and third part of the series today, where m where m dot is the mass flow rate of the fuel, that is measured in kg per second, or the mass going out of the rocket every second. Is the exit velocity, means velocity at the exit of the nozzle. Wherever the rocket nozzle ends, the whatever is the gas velocity there is called the exit velocity. A is the exit area of the nozzle, that is the exit cross section area of the nozzle. PE is the exit pressure, means pressure of the gases at the exit of the nozzle, that can not necessarily be equal to the ambient or the atmospheric pressure. It can be different, it can be same. So Then you have another very important term, that is the overall exhaust velocity, also called as ISP or the specific impulse, which measures the overall performance of a rocket engine, not only the propellant, but the whole rocket engine. I will explain you how do you compare two different propellants also in the later part of this course. Then this slide I don't think is of much use because as I already explained you. Let's come to the solid rocket motor. So this is how a solid rocket motor looks like what I think most of the amateur rocketry teams or yeah clubs in India are working on solids as of now, because India has a very strong foundation in solids than any other place in the world. So let's see what a solid rocket motor is consisting of. First thing you can see here is igniter. Igniter is basically something which is required to burn the propellant. I will explain you how it works. We will be talking first about the propellant grain. As I told you, solid in solid propellants, both oxidizer and fuel are in solid state. So and it is this part. This is the propellant. This is how it looks inside the rocket engine or the rocket motor. And why do you have an igniter? So I'll give you a very basic example. You have gas stove in your houses. When you turn on the gas stove, at least in India, when you turn on the gas stove, it does not catches fire on its own. What you have to do is give a spark with the help of a lighter or an ignition system. That lighter you can call it as an ignition system. So similar way for solid rocket also, it cannot burn on its own. It needs something which can burn, which can start the combustion. So you can take the analogy of the gas stove in your house, and similar way we want the solid propellant also. Then the motor casing is mostly made up of aluminum, or this motor casing, this part is mostly made up of aluminum or steel. And now I will explain you why do we have internal insulation here. Because if you search the melting point of aluminum or steel or even the super alloys, it is maximum 1000 Kelvin. It will melt over that temperature. And when the combustion is happening inside, means when the propellant is burning, the temperature produced inside the combustion chamber is, I will maybe write here, temperature is around 3300 Kelvin, and this metal melts at 1000 Kelvin. So this will definitely melt off. So you need something which has lower thermal conductivity, which cannot conduct the heat energy and absorbs most of it. That is called an insulation. That is a thermal insulator. And then I will explain you about the rocket. Actually, can I hide this? Yeah, this is nice. So then we have a rocket nozzle, a converging diverging nozzle. In today's session, in the later part, we will be understanding why do we have converging diverging nozzle and not only converging. This nozzle, I will tell you, I will give you a basic explanation. This nozzle, what it does is basically it converts the hot gases, the energy of the hot gases, that is thermal energy, into kinetic energy, that is it accelerates the gases. I will give you a basic example to get a physical feel of how nozzle works. So if you if you have a okay, you take your hand and open your mouth and try to blow air in your hand, then you will feel less force over your hand. But when you pluck your mouth, that is when you decrease the area from which the air is coming, and put this with the same pressure, you try to blow air on your hand, you will feel more pressure or more force. That gives you an understanding that when you decrease the area, initially your velocity of gases or speed of gases increases. So that is the simple concept of a rocket nozzle. It does the same thing. Basically, it decreases the area so that your velocity increases, and again increases the area to increase the velocity. That we'll be looking later. Why are we increasing the area? Next is the liquid rocket engine. So I could have showed you the actual liquid rocket engine how it looks, but you will be scared looking at the looking at the actual liquid rocket engine because it's very complicated. So that's why I put a simplified version of it, that is the schematics of a liquid rocket engine. And this is my work from ISRO, what I did at ISRO, so I can use and explain it in a better way. This is a staged combustion cycle. I will explain you what it is in a very simple way. Basically, you have a thrust chamber, that is the main engine. And in liquid, because you have both oxidizer and fuel, in the liquid side you need to pump it inside the chamber, store it separately, pump inside the chamber. So here there are storage tanks. This is for liquid oxygen, this is for liquid methane. Here it comes, the fuel comes from here, oxidizer comes from here. This is the pump. It means this is a pump fed system. As you know, in the villages, when you want to extract water from the ground, you need to create pressure. That happens with the help of a pump. So same thing is happening here. There is a pump which is increasing the pressure of the fluid. But to run the pump, you need electricity. But in rocket, getting electricity is difficult. So that is why we have a turbine. A turbine, when a turbine is rotated, it has a shaft connecting to the pump which rotates the pump at the required RPM, or the required angular speed. But how do you run the turbine now? So the turbine is run with the help of hot gases generated in the gas generator. Basically, you put a small amount of fuel and oxidizer in the gas generator, burn it, hot gases are produced, which runs the turbine. Turbine runs the pump, pumps, starts the flow of the fluid inside the combustion chamber. Same thing is happening in the oxygen line also. Same thing. You have a stabilizer here. So there are two parts here because this is a staged combustion cycle. The hot gases from gas generator are running the turbine, and the remaining hot gases are going in the combustion chamber again. So there are very less losses. The ISP is maximum in the staged combustion and full flow staged combustion cycles, or ISP recovery you can say. So I will just, this is about the liquid rocket engine, and other things you see are the valves. This is the gas generator flow rate control valve, this is the gas generator oxidizer control valve, injection valve, calibrated orifice, this is also calibrated orifice, injection valve, mixture ratio control valve. So these are the valves. This completes the small discussion on liquid. Now let's talk about hybrid rocket engines. If you have some doubt, you can note it as of now. Once the session is, I mean, once the first part of the session is over, then we can continue with the doubts. This is the hybrid rocket engine. This is also Asia's first student-built hybrid rocket engine. This is basically my design, my combustion chamber design of a hybrid rocket engine. You see, there is a injector bulkhead. Okay, change the color. There is an injector. Okay, yeah. There is an injector bulkhead over here. So I will tell you what happens in a hybrid. In solid, both were in solid state. Fuel oxidizer in liquid, both were in liquid state. Now, there has to be something in between. So we have hybrids. This is the solid fuel. All this can be made up of candle wax also. So candle burning is a hybrid rocket burning basically, for your reference. This is the fuel, and because fuel is in solid state, you can keep it in the chamber. But oxidizer it is not in solid state. So oxidizer is in liquid state. So you have to inject it from here. So that is why you have those pumping, plumbing system, everything behind it, and you have a injector to atomize the liquid, or just straight flow injectors for gaseous flow where you don't need atomization. This is the combustion chamber with the fuel. See, this also consists of the insulation like solid does. It has qualities of both solid and liquid. So in case you want to work on something in future which has solid liquid hybrid or a combination of something, then hybrid is the best thing for you to learn solid and liquid both at the same time. Now We have pre-combustion chamber and post-combustion chamber. There is basically these are void spaces, because when you inject the, I will tell you why a pre-combustion chamber is there. Because when you inject the fluid, then it is getting atomized, and in the pre-combustion chamber the fluid circulates or recirculates. That is called a recirculation zone. And when it is recirculating over there, the one with, because combustion is going on, there is heat energy also, and this recirculating gases are absorbing heat energy, and some molecules are getting activated, or the velocities or kinetic energy is increasing because of the because it is gaining temperature, it is getting excited, and those excited gases can only escape this recirculation zone and enter the combustion zone. The concept is, higher the initial temperature of the reactants, better is the performance, or higher is the overall temperature or total enthalpy release. This can be proved in basic thermodynamic courses, and that is why we have a pre-combustion chamber. Now, why do we have a post-combustion chamber? This area is very less. There is a boundary layer formation, viscosity, everything is there. Your combustion cannot be completed in a very small region. For combustion to complete, proper oxidizer fuel to mix properly, burn and release high temperature gases, you need more volume. That is why we have a post combustion chamber. That is a void space in which your oxidizer and fuel have plenty of time, that is a residence time, to mix with each other and produce high temperature gases. Then we have a rocket nozzle, same as a liquid or solid. This concludes our discussion on hybrid. I will just remove all the markings that I have done. Cool. This completes our discussion on solid liquid hybrid, the basic initial introduction. Now let's come on to the advantages of solid rocket motor. That is, it has a very simple design, very easy to operate. Just put an e-match and basically Diwali rocket. I forgot to give you the example. Diwali rocket is a solid rocket, and you know how easy it is to operate a Diwali rocket. Same way, I mean, the same difficulty level is for operating an actual solid rocket also. I mean, if you don't have any avionics or anything, just want to fly it, just burning the solid rocket motor has the same difficulty as a Diwali rocket, nothing more. It is ready to operate quickly. That is why it is used in most of the missile applications or military applications. There will be no leakage, no slosh, and it decreases the weight because both oxidizer and fuel are in solid state. There is no plumbing required. Just put them in a container and boom, fire. And very important part of solid rocket motor, why it is used in military application, is the shelf life. You can store a solid rocket propellant for over 15 to 25 years. And because you know, in the combat situation, if if if, if you, it's basically if the enemy is attacking your place, what you have to, you don't have time, you can't load a rocket, you can't fill the rocket engine with oxidizer, you don't have time. You, what you have to do is basically just load the rocket, the propellant in the rocket fast and fire. So that is why solids are mostly used in missile applications, military applications. Some of the propellants are non-toxic, clean exhaust. Okay, there is nothing called as sustainable clean propulsion. Everything has exhaust which is toxic. Even water and carbon dioxide as exhausts are producing global. I mean, they are increasing the global warming. So there is nothing called as non-toxic stuffs. It only depends when where are you firing it. For example, if you have a fluorine as exhaust gases or chlorofluorocarbons, if you are firing on Earth, it is very dangerous. But if you are firing in space, no worries, because there will be no bad effect of it. So it depends on the location where you are firing it. These were the advantages of solid rocket motor. Now let's talk about the disadvantages of a solid rocket motor. You know, Tipu Sultan's army, they were firing solid rockets on the enemy. And the story is, most of the soldiers of Tipu Sultan died not because of enemies' attack, but because of their own solid rockets blasting or exploding on the test bed. I mean, on the launch pad. So this proves that solid rocket motors explosion can be catastrophic. It can catch fire anytime, depending on the energy it is absorbing from the atmosphere. Transportation is very difficult because in solid rocket propellants you cannot have cracks. If you have a crack in solid rocket propellant or solid propellants, then gone. You can't basically, it will blast basically, or it will be performing in a, it's not a proper manner. So because the cracks increases because the combustion or the regression rate is pressure dependent. So the cracks can increase the burn surface area significantly, and hence i- it can cause a lot of catastrophic activities. And again, other reasons are same, like solid rockets you cannot transport. I mean, you have to ensure that during the transport there is no cracks or something, and you cannot operate in a variable temperature region. If you design a solid rocket propellant for 30 degree, you cannot operate it at 40 degrees. There will be variation in performance. You cannot, if you are designing a solid rocket to work from Ladakh, you cannot fire it at Rajasthan. It can even blast. There can be a lot of performance changes. Later in the course we will be looking in maybe the 20th or 30th lecture how these performance variations are coming from. You can actually derive the numbers of how this performance variation is coming. Liquid rocket, now coming on to the advantages of liquid rocket engines. So because in solid your oxidizer and fuel are together, so you cannot have high energetic oxidizer and fuel stored together because it can burst or blast anytime. In liquids, the specialty is both oxidizer and fuel are stored separately, so you can use any combination you want. That is why the specific impulse is higher here, or the performance parameter, that is a specific impulse, it is higher in liquids because you have the freedom to choose any oxidizer and fuel. In solids you do not, because even if it is, even if a propellant combination fuel oxidizer is highly perform, I mean having high ISP, but it may not be compatible. You touch each other and it blasts. You cannot have hypercolic compositions in solids, but you can have those things in liquids. So that is one of the benefit. The controllability. Liquids you can control the propulsion. Solids you cannot. You can throttle liquids. Solids you cannot. So that is one of the other thing. Liquids also, storable liquids has higher shelf life, and the major advantage of liquid is basically this thing, storage and throttability. That, for example, you need a satellite propulsion system which you can control. I will give you a very basic example. The Chandrayaan mission. When the Chandrayaan mission was happening, it was the Vikram lander was going on the moon. I see those small actuators, the vernier thrusters actuating more than 1,000 times. It means you need to start, stop, restart. That is pulse the engine. That capability solid cannot give, unfortunately. It can give, but because of the external conditions, that is the atmospheric radiation, etc., you do not want to use it. So, because it can have a performance variation. Liquids do not. So that is why we go with liquids. Disadvantages of liquids: toxicity. Whatever hypergolic liquids you have till date, everything is toxic in nature. Nothing is like, wherever it is used, the people have diseases, health diseases coming out for lifetime. So that is one of the major thing. And you have a lot of plumbing systems. So liquid engine designing is very complicated. You cannot do it. You have the problem of leakages. So even if your engine is theoretically very nice, if you have leakages, there is always practical problems. You can have leakages and your engine can perform I mean, it can shut off abruptly, or it can even blast, or anything can happen. So the complexity is high. And liquids, we have cryogenic storage points. There are cryogenic liquids that we are using for high performance. Those liquids storage is an issue. You have to create a thermally insulated environment, because I am also working on cryogenic propellants. So I know that problem. You have to store it in a temperature controlled environment, and basically you do not want any leakages, any thermal leakages, because then the material properties can be varied. Then the storage tanks can even blast because of the increase in temperature, because of thermal stresses in the chamber. And when you cryogenic liquids, when the temperature increases, it converts in gaseous state. Then again there is a high pressure and very pure chance that it will burn a blast off. Talking about the hybrid rocket motors advantages, it is very safe to handle. That is why I personally chose hybrid to work on in my bachelor life, because it's very simple, very simple. You can have cracks. I mean, you should not have leakages, but okay. But it is very simple because oxidizer fuel both are separate, so no chance of combustion or abrupt combustion. You have one oxidizer in liquid or gaseous state, fuel in solid state. So the complexity is also half of liquid. Modes of failure half than liquids. Combustion instability very low. No, I mean it just depends on the oxidizer mass flux you are operating at, but generally it's very low. You don't generally have instability in hybrid rockets until and unless you are not a good designer. Scalability, you can scale hybrids. I have scaled my hybrids from 200 newtons to 5 kilonewton, 5.4 kilonewton scale, and rest all things are, I mean, you can just read off. You can transport it, all those things, unlike solids, which are difficult to transport also. Disadvantages of hybrids: lower performance. Specific impulse is really low in hybrids, and regression rates. Basically, the rate at which the fuel burns, that is also very low because of the diffusion dominated flame combustion and boundary layer, the flame in the boundary layer. So this is one of the disadvantage which I consider. There is a potential chance of the combustion blowing out when the fuel is about to complete, leaving high sliver losses due to erosive burning also. So these are some of the problems with hybrids, and again, it requires multiple ignition systems. You can obviously make a hypergolic hybrid system, so that is not an issue. Talking a little bit on, okay, if this meeting is over, don't worry, I will be sending you another link of the meeting, so we will be having another meeting after this. So we will be talking now about high speed air breathing propulsion devices, that is ramjet and scramjet. The first image is basically to explain you how ramjet scramjets are built. So you have turbojet, you remove the compressor, remove the turbine, and yes, you have a ramjet. This operates basically, the compression is called as ram effect. That is why it is called as a ramjet, because the compression is due to the ram effect. And what is the difference between a ramjet and a scramjet? Both operates at supersonic speeds. Both operates at supersonic speed, supersonic slash hypersonic speeds. The only difference between ramjet and scramjet is the combustion velocity, the velocity of gases during the combustion. In ramjet, the when the fuel and oxidizer are burning, the velocity is subsonic. Subsonic means speed is lower than the speed of sound. In scramjet, when the combustion is happening, the speed is supersonic. The combustion speed is supersonic. That is more than the speed of sound. That is why scramjets can go to hypersonic speeds, and ramjets might go to hypersonic speeds. Yes, this is how a scramjet looks like. If you want, you can maybe take a screenshot of this. There is an airflow coming, oblique shock generations. There is no normal shock generation in, okay, yeah. There is no normal shock generation in scramjets, but there can be in ramjets, but you want to avoid it. If the work is going on with oblique shocks, then you have the flame holder over here. There are multiple sockets like this for flame holder, and then you have combustor and nozzle. This is the combustor. From here the nozzle starts. Basically you have an increasing area. This is a schematic of a scramjet, very basic scramjet. Let me, okay, yeah. Now let's talk 5 minutes on high speed propulsion devices based on combined cycles, that is RBCC, rocket based combined cycle engines. What you have here is, you have a you have a ejector based rocket system, you have a liquid rocket engine, you have a ramjet, you have a scramjet, and you have hybrid mode. Everything in a single engine. You have liquid rocket engine, scramjet, ramjet, ejector, hybrid. If this five things in a single rocket engine, that is called a combined cycle base. rocket engines, combined cycle based systems, that is RBCC, TBCC, DRBCC. This is a paper, a good paper on TRRE made by Chinese, that is turbo assisted rocket augmented ramjet scramjet engine. Very something on which not everyone in the world works on. Very less people in the world works on, but whoever works are valued a lot because this is the most complicated system in the history of propulsion. I don't want to talk about opportunities. Let's stop here. I'll stop the recording first.